Tonight, we're going to ask a question that might not have an answer. What lies beyond the farthest edge of the universe? Not just beyond the stars or the galaxies or even the cosmic microwave background, but past the very limits of space, time, and everything we think we know. Because here's what most people don't realize. The universe has an edge. Not a physical wall or a boundary you could touch, but a horizon beyond which nothing, not even light, can reach us. And what lies beyond that horizon is one of the most profound mysteries in all of science. By the end of tonight, you're going to explore everything from infinite space to parallel realities and confront the possibility that beyond might not even exist. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Let's start with what we know. The observable universe, the part of the cosmos we can actually see, is enormous. It stretches about 93 billion light-years across. That's the distance light has been able to travel in all directions since the Big Bang, accounting for the expansion of space itself. Inside this observable sphere, we have somewhere around 2 trillion galaxies, each containing hundreds of billions to trillions of stars. The numbers are so large they become meaningless. But the point is this: the observable universe is vast beyond human comprehension. But here's the critical thing to understand. The observable universe is not the entire universe. It's just the part we can see. And the reason we can only see this far has nothing to do with the power of our telescopes. It has to do with the age of the universe and the speed of light. Light travels at about 186,000 miles per second, or 300,000 kilometers per second. That sounds fast, and it is fast by human standards. Light could circle Earth's equator 7.5 times in a single second. It takes light only 1.3 seconds to reach the moon, just over 8 minutes to reach the sun. But the universe is so large and has been expanding for so long that there are regions of space whose light simply hasn't had time to reach us yet. The universe is 13.8 billion years old. That means light from distant regions has had 13.8 billion years to travel toward us. You might think that means we can see 13.8 billion light-years in all directions, making the observable universe about 27.6 billion light-years across. But it's more complicated than that. Space itself has been expanding during that time, which stretches the distance even further. When light left a distant galaxy 13 billion years ago, that galaxy might have been, say, 4 billion light-years away from us at the time. But during the 13 billion years it took that light to reach us, space was expanding, carrying that galaxy farther away. By the time the light reaches us today, that galaxy is now about 30 billion light-years away. The light has been traveling through expanding space, and the source of that light has been receding from us the entire time. This is why the observable universe is about 93 billion light-years across, rather than 27.6 billion. We're seeing light from galaxies that were once much closer but are now much farther because space has expanded in the intervening time. The result is a cosmic horizon, a boundary beyond which we cannot see. Not because there's nothing there, but because the light from those regions hasn't reached us yet, and in some cases, never will. The cosmic horizon is not a fixed distance. It's growing as the universe ages. Every second, light from slightly more distant regions reaches us for the first time, and the observable universe expands slightly. But here's the strange part. There are regions of space that we will never be able to see not because the light hasn't had time to reach us yet, but because space is expanding so fast that the light will never reach us. This is due to dark energy, the mysterious force driving the accelerating expansion of the universe. Galaxies beyond a certain distance are receding from us faster than the speed of light. Not because they're moving through space faster than light, which is impossible, but because the space between us and them is expanding faster than light can cross it. Light from these ultra-distant galaxies is being carried away from us by the expansion of space, like a swimmer trying to swim upstream in a river flowing faster than they can swim. The light makes progress toward us, moving through space at the speed of light, but the space itself is expanding faster in the opposite direction, so the light never gets closer. These regions are beyond what's called the cosmic event horizon, and we will never be able to observe them, no matter how long we wait. This horizon is sometimes called the particle horizon, or the cosmological horizon. It's the edge of the observable universe. Beyond it lies the unobservable universe, a region that exists, that contains matter and energy, galaxies and stars, but that we can never directly observe from our current location in space and time. Think of it like standing on a vast ocean. You can see to the horizon in all directions, but you know the ocean continues beyond what you can see. The observable universe is like that visible patch of ocean, and the cosmic horizon is like the point where the ocean meets the sky. Except in this case, the horizon isn't a fixed distance. It's determined by the age of the universe and the speed of light. So the first thing beyond the edge of the observable universe is simply more universe. More galaxies, more stars, more planets, more of the same stuff we see within our observable bubble. This unobservable universe might be finite, or it might be infinite. We don't know. If it's finite, it has some total size, some maximum extent. If you could somehow travel fast enough, you'd eventually reach a true edge, a place where space itself ends. But if it's infinite, then it goes on forever in all directions. No edge, no boundary, just more and more universe, extending infinitely. Both possibilities are mind-bending. A finite universe raises the question of what's outside it. If the universe has an edge, what's on the other side? But an infinite universe is equally strange. An infinite universe would contain an infinite number of galaxies, an infinite amount of matter and energy, and given enough space, an infinite number of copies of you reading this exact sentence right now. This isn't just speculation or science fiction. It's a mathematical consequence of infinity combined with a finite number of ways particles can arrange themselves. There are only so many ways atoms can be configured in a given volume of space. The number is enormous, unimaginably large, but it's still finite. If you have an infinite universe, then every possible configuration must repeat somewhere, and if it repeats once, it repeats infinitely many times. This means that in an infinite universe, there would be countless exact duplicates of our observable universe, each containing an exact duplicate of Earth, of you, of every moment of your life. The nearest such duplicate would be incomprehensibly far away, beyond not just our observable universe, but beyond trillions upon trillions of observable universes. The distance would be something like 10 to the power of 29 meters, a number so large it's meaningless, but it's not infinite. It's finite, which means in an infinite universe, there's a place where it exists. And between your nearest exact duplicate and you, there would be infinite variations. Universes almost like ours, but with tiny differences. A version where you chose a different career, where a different political party won an election, where the dinosaurs never went extinct, where Earth never formed. Every possible variation exists somewhere in the infinite expanse. The implications are profound and deeply strange. If the universe is infinite, then every possible version of your life is being lived somewhere out there right now. Every choice you didn't make was made by another version of you in another region of space. Every outcome you can imagine is real somewhere. This is one form of the multiverse hypothesis, the level 1 multiverse, where the universe is simply infinite and everything that can happen does happen somewhere. But we need to be careful here. Just because something is mathematically possible doesn't mean it's true. We don't know if the universe is infinite. Current measurements suggest it's very close to flat, which allows for the possibility of infinite size. But the measurements have uncertainty. The universe could be finite, but so large that the curvature is too small for us to detect. Let's explore the finite universe first. If the universe is finite, it has a specific shape and size. General relativity tells us that space itself can curve. A finite universe could curve back on itself, like the surface of a sphere. Imagine you're an ant walking on the surface of a balloon. You can walk in any direction, and you'll never reach an edge because the surface curves back on itself. It's finite in size. There's only so much surface area on the balloon, but it has no boundary. This is one possibility for the shape of our universe. It could be a three-dimensional analog of a sphere's surface, a shape that curves back on itself. If you traveled in one direction long enough, you'd eventually return to your starting point, like circumnavigating the globe. In this model, there is no edge in the traditional sense. The universe is finite but unbounded. There's no place where space ends, because space curves back on itself. But here's where it gets strange. What's outside this curved universe? Is there anything beyond the balloon? In the balloon analogy, we can picture the balloon floating in a room, surrounded by air and walls. But that's only because we're imagining a two-dimensional surface embedded in three-dimensional space. For a three-dimensional universe that curves back on itself, there is no outside. The universe isn't embedded in anything. It's all there is. The question, what's outside the universe, doesn't make sense, because outside implies a spatial relationship, and space only exists within the universe. This is one of the hardest concepts to grasp. We're used to thinking of objects as being inside other things, rooms inside buildings, buildings on planets, planets in space. But the universe itself isn't inside anything. It's the container, and there is no larger container. Some physicists describe it this way: the universe is not a thing in space. The universe is space. Space is a property of the universe, not something the universe exists within. But there's another possibility. The universe might not curve back on itself. It might be flat or nearly flat, which is what current measurements suggest. A flat universe could be infinite, extending forever in all directions. Or it could be finite, but with a more complex topology, like a three-dimensional version of a video game screen, where you exit one side and reappear on the other. If the universe is flat and infinite, then the unobservable universe is also infinite. Beyond our cosmic horizon lies an infinite expanse of galaxies and stars that we will never see. And in an infinite universe, some very strange things become not just possible, but inevitable. In an infinite universe, with a finite number of ways matter can arrange itself, every possible configuration must repeat infinitely many times. This means there would be an infinite number of exact copies of our observable universe scattered throughout the infinite expanse. Somewhere, infinitely far away, there's a region of space identical to ours, with an identical Milky Way, an identical Earth, and an identical you reading this exact script. Not just one copy, but infinite copies. And between those exact copies, there would be infinite variations. Versions where you made different choices, where history unfolded differently, where the laws of physics might even be slightly different. This is one implication of an infinite universe, and it's deeply unsettling. It suggests that every possible outcome of every possible event has occurred somewhere in the infinite cosmos. Every version of history, every conceivable reality exists. But we can never reach or observe these distant regions because they're beyond our cosmic horizon, and the expansion of space ensures they will always remain beyond our reach. Let's shift perspective and talk about what we can actually observe at the edge. The farthest we can see into space is the cosmic microwave background, the CMB. This is the afterglow of the Big Bang, radiation that has been traveling through space for 13.8 billion years. When we observe the CMB, we're seeing the universe as it was only 380,000 years after the Big Bang, long before galaxies or stars had formed. At that time, the universe was filled with hot, dense plasma, a soup of protons, electrons, and photons, all interacting with each other. The photons couldn't travel very far because they kept scattering off the electrons. It was like trying to see through fog. The universe was opaque to light. But as the universe expanded and cooled, eventually it reached a temperature where electrons and protons could combine to form neutral hydrogen atoms. This is called recombination, and it happened when the universe cooled to about 3,000 degrees Kelvin. When recombination occurred, photons suddenly had nothing to scatter off. The electrons were bound up in atoms, and neutral atoms don't interact with light as strongly as free electrons. The universe became transparent for the first time. Photons that had been trapped in the plasma were suddenly free to travel through space. Those photons have been traveling ever since, and today they reach us as the cosmic microwave background. But they've been redshifted by the expansion of space. When they were emitted, they were visible light photons with wavelengths corresponding to the 3,000-degree temperature of the plasma. But space has expanded by a factor of about 1,100 since then, stretching the wavelengths of the photons by the same factor. Today, these photons have wavelengths in the microwave range, corresponding to a temperature of about 2.7 degrees Kelvin. The CMB is everywhere. If you could see microwaves, the entire sky would glow with this faint radiation. It's the oldest light in the universe, and it carries information about the early cosmos. The CMB was first detected accidentally in 1964 by Arno Penzias and Robert Wilson, two radio astronomers working at Bell Labs. They were trying to eliminate noise from their antenna and kept detecting a persistent background hiss that came from all directions. At first, they thought it was interference, maybe from nearby New York City or even from pigeon droppings on their antenna. But after cleaning the antenna and eliminating all known sources of noise, the signal remained. It was coming from space, and it was uniform in all directions. Meanwhile, physicists at Princeton University, led by Robert Dicke, had been developing the theory of the Big Bang and had predicted that if the universe began in a hot, dense state, there should be leftover radiation with a temperature of a few degrees Kelvin. When Penzias and Wilson heard about this prediction, they realized they had discovered the cosmic microwave background. Their discovery was one of the most important confirmations of the Big Bang theory and earned them the Nobel Prize in Physics in 1978. The CMB marks the edge of the observable universe in a very real sense. It's the oldest light we can ever see. Before the CMB, the universe was opaque, filled with hot, dense plasma that light couldn't travel through. So we can't see anything before that era, no matter how powerful our telescopes become. We can infer what happened before recombination using physics and mathematics, but we can't directly observe it with light. The CMB is our cosmic horizon in time. Beyond it, the universe exists, but we can't observe it with electromagnetic radiation because light couldn't travel freely yet. But here's something remarkable. The CMB is not perfectly smooth. When we look at it with high-precision instruments, we see tiny fluctuations in temperature, tiny variations from one region to another. These fluctuations are incredibly small, only about 1 part in 100,000. If the average temperature is 2.725 Kelvin, the fluctuations are about 27 microkelvin, 27 millionths of a degree. But those tiny fluctuations contain an enormous amount of information. They're the seeds from which all structure in the universe grew. Regions that were slightly denser than average attracted more matter through gravity. Over hundreds of millions of years, these overdense regions collapsed to form the first galaxies and eventually galaxy clusters and the cosmic web we see today. The fluctuations in the CMB are like a blueprint for the universe. They tell us how matter was distributed in the early cosmos, and they allow us to predict how that matter evolved into the structures we see today. We can measure the properties of these fluctuations with incredible precision. Satellites like COBE in the 1990s, WMAP in the 2000s, and Planck in the 2010s have mapped the CMB across the entire sky with ever-increasing resolution and sensitivity. These maps have allowed us to measure cosmological parameters with percent-level precision. We know the age of the universe to better than 1% accuracy, 13.77 billion years. We know the composition of the universe, how much is normal matter, and dark energy, to a few percent. We know the rate of expansion, the Hubble constant, though there's currently some tension between measurements from different methods. We know the geometry of space is flat to within a tiny margin of error. All of this from studying tiny temperature fluctuations in the microwave background. The CMB has been called the most perfect scientific dataset. It's a snapshot of the entire visible universe from a single moment in time, 13.8 billion years ago. And it matches the predictions of the Big Bang plus inflation model to extraordinary precision. The pattern of fluctuations, the statistical properties, the angular scale at which they appear, all of it matches what we expect if inflation generated quantum fluctuations that were stretched to cosmic scales and then grew through gravitational collapse. But the CMB also raises questions that we're still trying to answer. There are some anomalies, features in the data that don't quite match the standard model. For example, there's a cold spot, a region of the sky where the CMB is slightly colder than expected. It might be a statistical fluke, or it might be a sign of something interesting, like a supervoid, a huge underdense region of space between us and the CMB. Or it might be evidence of something even stranger, like a collision with another bubble universe before our observable region formed. If two bubble universes collided during inflation, the collision would leave a circular imprint in the CMB, a region with a specific pattern of temperature fluctuations. Searches for such signals have been conducted, and while a few candidates have been found, none are statistically significant enough to claim a detection. The question remains open. There's also the horizon problem that inflation was designed to solve. When we look at opposite sides of the sky, we see regions of the CMB that are separated by 93 billion light-years today. But those regions have never been in causal contact in the standard Big Bang model without inflation. Light from one region hasn't had time to reach the other region. So how do they have the same temperature to 1 part in 100,000? How did they know to have the same properties? Inflation solves this by saying those regions were in causal contact before inflation, when they were very close together. Inflation then stretched them to opposite sides of the observable universe, but they retain the same properties because they were once in contact. Without inflation, the uniformity of the CMB is a mystery. With inflation, it's a natural consequence. The CMB is also our best window into the very early universe. By studying the polarization of the microwave background, we can search for gravitational waves produced during inflation. These primordial gravitational waves would leave a specific imprint, a twist in the polarization pattern called B modes. Several experiments are searching for this signal right now. If we detect it, it would confirm inflation and tell us about the energy scale at which it occurred. It would be one of the most important discoveries in cosmology. So the CMB is not just the edge of the observable universe. It's a treasure trove of information about the Big Bang, inflation, the geometry of space, the composition of the universe, and possibly even hints of what lies beyond our cosmic horizon. Every measurement we make of the CMB gives us a clearer picture of how the universe began and how it evolved into what we see today. The answer, according to our best theories, involves something called inflation. Inflation is the idea that the universe underwent a period of exponential expansion in the first fraction of a second after the Big Bang. During inflation, the universe expanded faster than the speed of light, not because anything was moving through space faster than light, but because space itself was expanding. This is an important distinction. Special relativity says that nothing can move through space faster than light, but it says nothing about how fast space itself can expand. Space can expand at any rate, and during inflation, it expanded exponentially fast. Inflation lasted only a tiny fraction of a second, something like 10 to the negative 32 seconds. But in that time, the universe expanded by a factor of at least 10 to the 26, and possibly much more. Some models suggest the expansion factor could be as large as 10 to the 100 or even higher. A region smaller than an atom became larger than the observable universe today. This exponential expansion solved several problems in cosmology. It explained why the universe appears so uniform in all directions. Before inflation, different regions of the early universe hadn't had time to interact with each other, to come into thermal equilibrium. But inflation stretched a tiny region, one that was small enough to have equilibrated to cosmic scales. So the entire observable universe today came from a region that was once small enough for all its parts to have the same temperature and properties. This explains the homogeneity we observe in the cosmic microwave background. Inflation also explained why the universe appears so flat. Any curvature that existed before inflation would have been stretched out, flattened, like the surface of a balloon when you inflate it. A curved surface looks flatter and flatter as you expand it. After inflation, the universe would be so close to flat that we couldn't measure the curvature. And inflation explained why we don't observe certain exotic particles that early universe physics predicts should have been created. Particles like magnetic monopoles, which should have been produced in the hot, dense conditions of the Big Bang, would have been diluted to undetectable levels by the exponential expansion. But inflation also did something else, something perhaps even more important. It generated the tiny quantum fluctuations that became the seeds of all cosmic structure. Before we understand how, we need to understand what quantum fluctuations are. In quantum mechanics, there's a fundamental limit to how precisely we can know certain pairs of properties. This is the Heisenberg uncertainty principle. One consequence is that energy and time have an uncertainty relationship. For very short time intervals, energy can fluctuate wildly. Virtual particles can pop into existence, borrowing energy from the vacuum, as long as they disappear quickly enough that the borrowed energy is paid back. These quantum fluctuations are happening everywhere, all the time, at the smallest scales. Normally, they don't affect macroscopic reality. They're too small, too short-lived. But during inflation, something remarkable happened. The exponential expansion of space stretched these tiny quantum fluctuations to cosmic sizes faster than they could disappear. A quantum fluctuation that started out smaller than the Planck length, the smallest meaningful distance in physics, was stretched to the size of galaxies or even larger. When inflation ended, these stretched quantum fluctuations became classical fluctuations in the density of matter and energy. Regions that had a tiny quantum excess of energy became regions with slightly more matter than average. Regions with a quantum deficit became regions with slightly less matter, and those fluctuations are what we see in the CMB. They're what eventually became galaxies, stars, planets, and us. The evidence for inflation comes from several sources. First, the CMB fluctuations have a specific pattern predicted by inflation. They're nearly scale invariant, meaning they have roughly the same amplitude at different scales, and they're Gaussian, meaning they follow a specific statistical distribution. These properties match what inflation predicts and are difficult to explain otherwise. Second, inflation predicts that the universe should be very close to flat, and measurements of the CMB confirm this to high precision. The universe's curvature, if it exists, is less than 1%, consistent with a perfectly flat universe. Third, inflation predicts that gravitational waves should have been produced during the inflationary period, ripples in space-time itself that propagate through the universe. These primordial gravitational waves would leave a specific imprint on the CMB, a pattern called B-mode polarization. Detecting this signal is one of the major goals of modern cosmology. Several experiments are searching for it right now. If we find it, it would be smoking gun evidence for inflation and would tell us about the energy scale at which inflation occurred. During inflation, quantum fluctuations, tiny random variations in energy at the smallest scales, were stretched to cosmic sizes by the rapid expansion of space. When inflation ended, these quantum fluctuations became classical fluctuations in density, regions that were slightly more or less dense than average. And those fluctuations are what we see in the CMB. They're what eventually became galaxies, stars, planets, and us. In a very real sense, the structure of the universe, including the existence of Earth and everything on it, traces back to quantum randomness during the first fraction of a second after the Big Bang. The universe as we know it emerged from quantum noise amplified to cosmic scales by inflation. That's remarkable and deeply strange. But inflation also has implications for what lies beyond the edge of the observable universe. If inflation happened, and the evidence strongly suggests it did, then the universe is almost certainly much larger than the part we can see. Inflation would have expanded the universe to a size vastly larger than our observable horizon. In fact, most models of inflation predict that the universe is effectively infinite or so large that it might as well be. So the region beyond our observable universe, the unobservable universe, is almost certainly enormous, possibly infinite, and filled with galaxies and structure that we will never see. But inflation raises another possibility, one that's even stranger. Some versions of inflation, called eternal inflation, suggest that inflation never completely stops everywhere. Instead, inflation ends in some regions, creating bubble universes like ours, but continues in other regions, spawning new bubble universes indefinitely. In this model, our observable universe is just one bubble in an infinite sea of bubbles, each one a separate universe with its own properties. This is one version of the multiverse hypothesis. The multiverse is the idea that our universe is not the only one. There could be countless other universes, each with different physical laws, different constants of nature, different structures. Some might be similar to ours, others radically different. Some might have stars and galaxies, others might be empty or filled with exotic matter. Some might have 3 dimensions of space like ours, others might have more or fewer dimensions. In eternal inflation, each bubble universe forms when inflation ends in a particular region. Inside the bubble, inflation stops and the energy driving inflation decays into matter and radiation. This is what creates the hot, dense state we call the Big Bang. But outside the bubble, inflation continues, and more bubbles form. This process happens over and over, creating an infinite multiverse of bubble universes. Each bubble is causally disconnected from the others. Light and information cannot travel from one bubble to another because the space between them is expanding faster than light due to ongoing inflation. So, if the multiverse exists, we could never observe other universes directly. They're not just beyond our observable horizon. They're in a completely separate region of the multiverse, isolated from us forever. But here's where it gets really interesting. In eternal inflation, the laws of physics might be different in each bubble universe. The laws we observe, the strength of gravity, the mass of the electron, the speed of light, these might not be fundamental constants of nature. They might be environmental variables that take different values in different bubble universes. This idea comes from string theory, which predicts something called the landscape. String theory requires extra dimensions beyond the 3 spatial dimensions we experience. These extra dimensions can curl up in different ways, and each different configuration leads to a different set of physical laws in the resulting 3-dimensional universe. The number of possible configurations is enormous, perhaps 10 to the 500 or more. Each one represents a possible universe with different properties. In some universes, electrons might be heavier. In others, the strong nuclear force might be weaker. In others, there might be additional forces or particles we don't have in our universe. Most of these universes would be hostile to life as we know it. If the strong nuclear force were slightly weaker, atomic nuclei wouldn't hold together, and chemistry as we know it couldn't exist. If it were slightly stronger, stars might burn too quickly or not form at all. If gravity was stronger, stars would collapse into black holes before planets could form. If it were weaker, matter might never clump together to form galaxies. If the electromagnetic force had a different strength, atoms might not be stable or might not form molecules. The laws of physics in our universe appear to be finely tuned for the existence of complex structures like stars, planets, and living things. This is sometimes called the fine-tuning problem. Why do the constants of nature have the values they do? Why are they in the narrow range that allows for stars, galaxies, planets, and life? One answer is the anthropic principle. We observe a universe with these particular laws because only in such a universe could observers exist to make observations. If the laws were different, we wouldn't be here to ask the question. In a multiverse with different laws in different regions, this makes sense. Most universes in the multiverse would be empty or filled with structureless matter. But in a tiny fraction of universes, the laws happen to allow for complexity. And only in those universes do observers arise to wonder about the laws of physics. We find ourselves in one of the rare life-friendly universes, not because the laws were designed for us, but because we could only exist in such a universe. This is a controversial idea. Some physicists find it deeply unsatisfying because it doesn't explain why the laws have the values they do in our universe. It just says that in a multiverse, all values exist somewhere, and we happen to be in one where the values allow life. Others argue that the anthropic principle is a legitimate form of explanation, similar to explaining why Earth has liquid water, by noting that only planets in the habitable zone have liquid water, and only on such planets could life evolve to ask the question. The debate continues, but the fact that inflation naturally leads to a multiverse, and that string theory predicts a landscape of possible laws, suggests that the multiverse might be more than speculation. It might be a consequence of our best theories of the universe. This raises profound questions about what it means for something to exist. If other universes are completely unobservable, if they can never affect us in any way, do they really exist? Or are they just mathematical constructs, predictions of our theories that have no physical reality? This is where physics starts to blend into philosophy. It's a question that has occupied philosophers for millennia. What does it mean for something to exist? In science, we typically say something exists if it can be observed, or if it has observable consequences. An electron exists because we can detect it and measure its properties. A black hole exists because we can see its gravitational effects on nearby matter and detect the gravitational waves when two black holes merge. But what about things that have no observable consequences? What about regions of space beyond our cosmic event horizon that we can never see or interact with? What about other bubble universes in eternal inflation that are forever isolated from us? What about parallel worlds in the many worlds interpretation of quantum mechanics? Some physicists argue that if a theory makes testable predictions in our universe, and those predictions turn out to be correct, then we should take the theory seriously, even if it also predicts things we can't observe, like other universes. Inflation makes testable predictions about the cosmic microwave background. It predicts the universe should be flat, that the fluctuations should be nearly scale, invariant and Gaussian, that there should be primordial gravitational waves. These predictions match observations. So if inflation is correct in the things we can test, maybe we should trust it about the things we can't test, like the existence of a vastly larger universe beyond our horizon, or a multiverse of bubble universes. This is an argument from theoretical consistency. The theory works where we can test it, so we accept its other predictions even if we can't test them. String theory uses a similar argument. If string theory successfully unifies gravity with the other forces and makes predictions that turn out to be correct, then we might accept its predictions about extra dimensions and the landscape of possible universes even if we can't directly observe those things. Others argue that science is fundamentally about what we can observe and test, and predictions about unobservable universes are not science. They're speculation, mathematics, perhaps interesting philosophy, but not empirical science. This view holds that existence claims should be grounded in observability. If something can never be observed, even in principle, then calling it real is meaningless. The debate is ongoing, and it cuts to the heart of what science is and how we should interpret our theories. There's also the question of what we mean by observation. We can't directly observe electrons. They're too small. We observe their effects, the tracks they leave in detectors, the way they deflect in magnetic fields, the patterns they create in scattering experiments. From those observations, we infer the existence of electrons and measure their properties. Similarly, we can't directly observe the interior of the sun. We observe the light it emits and the neutrinos that escape from its core. And from those observations, we infer what's happening inside. So observation doesn't always mean direct visual perception. It means having some causal connection, some way for the thing we're studying to affect our instruments or our senses. The question is whether we should extend existence claims to things that have no causal connection to us whatsoever. Not now, not ever, not even in principle. The edge of the observable universe represents the boundary of causal connection. Beyond that boundary are regions that cannot affect us because their light will never reach us. If we accept that those regions exist simply because the laws of physics that apply here should apply there, then we're making an inference based on theoretical consistency rather than direct observation. And that opens the door to accepting other inferences based on theoretical consistency, like the multiverse or parallel worlds. There's a related question about the nature of mathematical truth. The laws of physics are expressed in mathematics. General relativity is a set of equations relating the curvature of space-time to the distribution of matter and energy. Quantum mechanics is a mathematical framework for calculating probabilities of measurement outcomes. When we say these theories are true, what do we mean? Do we mean they're accurate descriptions of an independently existing reality? Or do we mean they're useful tools for making predictions? If the mathematics of our theories predicts unobservable universes, does that mean those universes exist? Or does it just mean the math extends beyond the domain where it can be empirically verified? Platonists would argue that mathematical structures have a kind of existence independent of the physical world. The number 3 exists whether or not there are 3 of anything. The equations of general relativity exist whether or not there's a universe to obey them. In this view, if the mathematics of eternal inflation or the many worlds interpretation is logically consistent and follows from our best theories, then the multiverse or parallel worlds exist in some sense, whether or not we can observe them. Others would argue that mathematics is a human invention, a language we use to describe patterns in nature. The math itself doesn't create reality. Reality comes first, and we invent math to describe it. In this view, mathematical predictions about unobservable regions are just extrapolations that may or may not correspond to anything real. These are deep philosophical questions without clear answers. But they matter because they affect how we think about the universe and our place in it. If the universe is finite and bounded by the observable horizon, then we can potentially understand everything that exists. The totality of reality is, in principle, knowable. But if the universe is infinite, or if there's a multiverse, or if there are parallel worlds, then the totality of reality vastly exceeds what we can ever know. Most of existence would be forever hidden from us. That's a humbling thought. It would mean that science, for all its power and success, is fundamentally limited. There are questions we can never answer, not because we lack the technology or intelligence, but because the answers lie beyond the boundary of what can be observed. But it's also a liberating thought. It means reality is richer and more complex than we can imagine. It means there's always more to discover, more mysteries to ponder, more frontiers to explore. The edge of the universe is not just a physical boundary. It's a boundary between knowledge and mystery, between what we can know and what we can only wonder about. And throughout history, humanity has pushed against those boundaries. We've extended our vision with telescopes, our understanding with mathematics, our reach with spacecraft. We've gone from thinking Earth was everything to discovering we're on a planet orbiting a star in a galaxy, in a universe that might be one among countless others. Each expansion of our cosmic perspective has been humbling. We're smaller than we thought, less central, less special. But each expansion has also been empowering. We can understand more than we thought. We can see farther, think deeper, ask bigger questions. The edge of the universe represents the current limit of that expansion. It's where our understanding ends and speculation begins. But it's not a permanent limit. As our theories improve and our observations become more precise, the boundary shifts. Questions that were once purely philosophical become scientific. Things that were once unobservable become observable. The edge moves and our knowledge grows. There's another version of the multiverse, one that doesn't rely on inflation. It comes from quantum mechanics. In quantum mechanics, particles don't have definite properties until they're measured. Before measurement, a particle exists in a superposition, a combination of all possible states. An electron can be spinning up and spinning down at the same time. A photon can be polarized vertically and horizontally simultaneously. A particle can be in multiple places at once. This isn't just uncertainty about which state the particle is in. The particle genuinely exists in all states simultaneously until measurement forces it to pick one. When you measure the particle, the superposition collapses and the particle takes on a definite state. This is called wave function collapse, and it's one of the most mysterious aspects of quantum mechanics. Nobody fully understands what causes collapse or why measurement is special. The act of measurement somehow forces the quantum system to choose one outcome from all the possibilities. But there's a version of quantum mechanics called the many worlds interpretation that suggests the superposition doesn't actually collapse. Instead, every time a quantum measurement happens, the universe splits into multiple branches, one for each possible outcome. In one branch, you measure the particle in one state. In another branch, you measure it in a different state. Both branches are real. Both exist, but they're separate. You only experience one of them. The idea was first proposed by Hugh Everett in 1957. Everett was a graduate student at Princeton, and his many worlds interpretation was part of his doctoral thesis. At the time, it was considered radical and was largely ignored by the physics community. But, over the decades, it has gained support because it solves several conceptual problems in quantum mechanics without adding anything new to the mathematics. In the many worlds interpretation, the Schrödinger equation, the fundamental equation of quantum mechanics, always holds. There's no special collapse process that violates the equation during measurement. The wave function never collapses. It continues to evolve smoothly, describing all possible outcomes. But what we perceive as collapse is actually the universe branching into separate realities. If the many worlds interpretation is correct, then every quantum event creates new branches of reality. And since quantum events are happening constantly, everywhere in the universe, the number of branches is growing exponentially. Every radioactive decay, every photon emitted or absorbed, every quantum fluctuation in every atom, each one creates new branches. There would be an unimaginably vast, possibly infinite number of parallel universes, each one representing a different outcome of quantum events. In some of these universes, you made different choices. The decision to read this script or do something else was a macroscopic event, but it might have been influenced by quantum processes in your brain. In some branches, you made one choice. In others, you made a different choice. In some universes, history unfolded differently. Maybe a mutation in a key historical figure's DNA, a quantum event, led to a different personality and different decisions that changed the course of history. In some universes, the asteroid that killed the dinosaurs 65 million years ago missed Earth due to a quantum fluctuation affecting its trajectory billions of years earlier. In those branches, dinosaurs might still exist, and mammals, including humans, might never have evolved. In some universes, the laws of physics might be slightly different if those laws themselves depend on quantum outcomes during the early universe. The many worlds interpretation is controversial. Many physicists find it extravagant. It requires accepting that an infinite number of parallel universes exist, most of which we can never observe or interact with. It seems to violate Occam's razor, the principle that we should prefer simpler explanations. How can a theory that multiplies the number of universes infinitely be considered simple? But supporters of many worlds argue that it's actually the simplest interpretation of quantum mechanics because it doesn't add anything to the theory. The standard Copenhagen interpretation requires adding a collapse process that happens during measurement. That's an extra assumption, an extra mechanism that's not in the Schrödinger equation. Many worlds just says the Schrödinger equation always holds. Everything else follows from that. The branching of reality is a consequence, not an assumption. From a mathematical standpoint, many worlds is elegant. From a philosophical standpoint, it's bizarre. It says that every possible outcome of every quantum event actually happens in some branch of reality. Nothing is truly random in many worlds. Every possibility is realized. When you flip a quantum coin, both outcomes occur. The universe branches, and in one branch it's heads, in the other it's tails. Both versions of you exist, each experiencing a different outcome. The randomness we observe in quantum mechanics is not fundamental randomness, it's subjective branching. You can't predict which branch you'll find yourself in, but all branches exist. If many worlds is correct, then the question of what's beyond the edge of our universe has another answer. Beyond our universe lie infinite parallel realities, branching from every quantum event, each one as real as ours, each one inaccessible to us. This is sometimes called the Level 3 multiverse, the quantum multiverse, distinct from the Level 1 multiverse of an infinite universe and the Level 2 multiverse of bubble universes from eternal inflation. And all three might exist simultaneously. The universe might be infinite, containing infinite copies of our observable universe. Eternal inflation might create bubble universes with different laws, and quantum mechanics might create branching realities. Each level of multiverse is independent and could exist whether the others do or not. If it's correct, then beyond the edge of our universe, there's not just more space or other bubble universes. There's an infinite branching tree of realities, each one as real as ours, each one inaccessible to us. Let's step back and consider what all this means for the question of what's beyond the edge. We have several possibilities, and the truth might involve more than one of them. First, beyond the observable universe is simply more universe. More galaxies, more stars, more space, extending far beyond what we can see. This unobservable universe might be finite or infinite. We don't know. Second, if the universe is finite and curved, then there might be no beyond at all. The universe curves back on itself, and there's no outside. The concept of beyond doesn't apply. Third, if eternal inflation is correct, then beyond our observable universe lies an inflating multiverse, an infinite expanse giving birth to bubble universes, each one a separate cosmos with its own laws and structures. Fourth, if the many worlds interpretation of quantum mechanics is correct, then beyond our universe lie infinite parallel realities, branching from every quantum event. And finally, there's the possibility that we're missing something fundamental. Our theories, general relativity, and quantum mechanics break down at the very beginning of the universe. At the Big Bang singularity, the equations give infinite answers, which means they're not describing reality correctly. We need a theory of quantum gravity, a theory that unifies general relativity and quantum mechanics to understand what really happened at the beginning of the universe and what might lie beyond the edge. String theory is one attempt at such a theory. In string theory, the fundamental building blocks of reality are not particles, but tiny vibrating strings. These strings are incredibly small, about the Planck length, which is 10 to the negative 35 meters. That's so small that if an atom were enlarged to the size of the solar system, a string would still be smaller than a tree. Different vibrations of these strings correspond to different particles and forces. An electron is one vibration pattern, a photon is another, a quark is another. All particles are just different notes played on the same fundamental strings. String theory requires extra dimensions of space beyond the three we experience. In the most studied version, called superstring theory, there are 9 spatial dimensions plus 1 time dimension, for a total of 10 dimensions. But we only experience 3 spatial dimensions. Where are the other 6? The standard answer is that they're curled up very small, compactified into shapes too tiny to detect directly. Imagine a garden hose. From far away, it looks one-dimensional, like a line, but up close, you can see it has thickness. There's a second dimension, curled up into a small circle around the hose. Similarly, the extra dimensions in string theory might be curled up at every point in space, forming tiny geometric shapes called Calabi-Yau manifolds. These shapes are complex, with multiple curled-up dimensions folding through each other in intricate patterns. The exact shape of these compactified dimensions determines the physics we observe in the 3 large dimensions. Different Calabi-Yau shapes lead to different particle properties, different forces, different constants of nature. And there are an enormous number of possible shapes, possibly 10 to the 500 or more. Each one represents a different vacuum state, a different possible universe with different laws of physics. This is the string theory landscape, and it's one reason why eternal inflation and the multiverse are taken seriously. If string theory is correct, and there are 10 to the 500 possible vacuum states, and if eternal inflation creates bubble universes, then different bubbles might have different compactifications of the extra dimensions and therefore different physical laws. The landscape would be populated. Every possible universe would exist somewhere in the eternal multiverse. But string theory also allows for another possibility. In some versions, there could be large extra dimensions that we haven't detected yet. Our entire observable universe, everything we can see and measure, might be confined to a three-dimensional brain, a membrane embedded in a higher dimensional space called the bulk. It's like we're living on the surface of a sheet of paper floating in a three-dimensional room. We can move around on the paper, but we can't step off it into the room. All the particles and forces we know about, except gravity, would be confined to our brain. Gravity, however, might leak into the bulk, into the extra dimensions. This could explain why gravity is so much weaker than the other forces. The electromagnetic force is about 10 to the 30, 6 times stronger than gravity. That's an enormous difference, and it's never been fully explained. But if gravity can spread out into extra dimensions while the other forces are confined to our three-dimensional brain, then gravity would be diluted. It would appear weaker in our three dimensions because its strength is shared with the extra dimensions. This Brainworld scenario leads to some fascinating possibilities. There might be other brains floating in the bulk, other three-dimensional universes parallel to ours. We couldn't see them or interact with them directly because photons and matter are confined to our brain. But gravity would leak between brains, and if two brains collided, the energy of the collision could create what we perceive as a Big Bang. Some cosmologists have proposed that the Big Bang wasn't the beginning of time, but rather a collision between brains in the higher dimensional bulk. Our universe would have a pre-Big Bang history, a time when our brain existed before the collision. This is speculative, but it's consistent with some versions of string theory, and it solves the problem of the Big Bang singularity. If the Big Bang was a brain collision rather than a true singularity, then physics doesn't break down at the beginning. We can describe what happened before and during the event using string theory. The problem with string theory, and it's a significant problem, is that we can't test most of these predictions. The strings themselves are too small to observe directly. The extra dimensions, if compactified, are too small to detect. The landscape of 10 to the 500 vacua can't be explored experimentally. We can't build particle accelerators powerful enough to reach the energy scales where string theory's predictions differ from standard physics. And we certainly can't observe other brains in the bulk or watch bubble universes forming in eternal inflation. This has led to a debate within physics about whether string theory is science or philosophy. If a theory makes no testable predictions, is it really a scientific theory? Supporters of string theory argue that it does make predictions, just not ones we can test with current technology. And they argue that it's the only known candidate for a complete theory of quantum gravity, the only framework that unifies all the forces and explains gravity at the quantum level. Critics argue that a theory that can't be tested isn't useful, and that physics should focus on ideas that make predictions we can verify. The debate continues, but string theory remains the most developed approach to quantum gravity, and many of the brightest minds in physics are working on it. Whether it's correct or not, we don't know. But it's one possible answer to the question of what lies beyond the edge of the universe. Extra dimensions, other brains, bubble universes in a higher dimensional bulk, all arising from the mathematics of vibrating strings. Loop quantum gravity is another approach to quantum gravity. Instead of strings, It describes space itself as being made of discrete chunks, tiny quantum loops of space-time. At the smallest scales, space is not smooth and continuous, but granular, like pixels on a screen. The basic idea is that space-time has a minimum size, the Planck scale, and you can't subdivide it further. Space is quantized, just like energy is quantized in quantum mechanics. In loop quantum gravity, space is woven from tiny loops, each one about the Planck length across. These loops are like the threads in a fabric, and space-time is the fabric they weave. The loops connect to each other in a vast network called a spin network, and the geometry of space emerges from how these loops are connected. When matter and energy are present, they curve the spin network, creating what we experience as gravity. Loop quantum gravity makes specific predictions about the early universe. It suggests that the Big Bang singularity might not be a true singularity. Instead, it might be a bounce. In classical general relativity, the Big Bang is a point of infinite density where the equations break down. But in loop quantum gravity, there's a maximum density that matter can reach. When the universe contracts to that maximum density, quantum effects create a repulsive force that stops the collapse and causes the universe to bounce back, transitioning from contraction to expansion. This quantum bounce replaces the Big Bang singularity with a smooth transition. If this is correct, then beyond the Big Bang, before our universe began, there might have been a previous universe, a previous cycle. The universe could have been contracting for billions of years, growing denser and denser, until it reached the Planck density and bounced. Our Big Bang would be the moment of the bounce, the transition from contraction to expansion. And before that, there could have been another cycle, and another, possibly infinitely, into the past. This is the idea of a cyclic universe, a cosmos that goes through infinite cycles of expansion and contraction. Each cycle could last billions or trillions of years. Each could have different properties, different distributions of matter, possibly even different physical constants if the bounce process resets certain parameters. The cyclic model solves some problems in cosmology. It eliminates the Big Bang singularity by replacing it with a bounce. It explains why the universe appears so uniform, because the contraction phase would have smoothed out irregularities. And it avoids the question of what caused the Big Bang, because the Big Bang wasn't the beginning. It was just a transition between cycles. But the cyclic model has its own challenges. For the bounce to work, for the contraction to reverse into expansion, you need specific quantum effects that we haven't fully confirmed. The mathematics of loop quantum gravity is complex, and it's not yet clear whether the bounce happens in all scenarios or only under special conditions. There's also the entropy problem. The second law of thermodynamics says that entropy, disorder, always increases. In each cycle, the universe should become more disordered. Over infinite cycles, the universe should have reached maximum entropy by now, a state called heat death, where everything is uniformly spread out and no structure remains. But we observe structure, galaxies, stars, temperature differences. The universe is not in heat death. So either the cyclic model is wrong, or there's some process that resets entropy during each bounce, or the universe hasn't been cycling infinitely. Maybe the cycles started a finite time ago, or maybe entropy increases in a way that allows structure to persist across cycles. These are open questions, and cosmologists are working to resolve them. Another version of the cyclic model comes from string theory. In this version, two branes collide periodically in the higher dimensional bulk. Each collision creates a burst of energy that we perceive as a Big Bang. After the collision, the brains separate and the universe expands and cools. Eventually, they're pulled back together by forces in the bulk, and they collide again, starting a new cycle. This ekpyrotic scenario, named after the ancient Greek idea of cosmic cycles, combines elements of string theory with the cyclic universe concept. It predicts specific patterns in the cosmic microwave background that might be detectable, giving us a way to test the idea. But again, we need more data before we can say whether the cyclic model in any of its forms is correct. Right now, it's a fascinating possibility, but it's not confirmed. But all of these ideas, the multiverse, extra dimensions, the cyclic universe, they're speculative. We don't have direct evidence for any of them. They're predictions of our theories, extensions of our mathematics, attempts to answer questions that observations can't yet address. But there's one aspect of what lies beyond the edge that we can observe directly, and it's deeply mysterious: dark energy. In 1998, two teams of astronomers made a discovery that shocked the physics community. They were measuring the distances to distant supernovas, exploding stars that can be used as standard candles to measure cosmic distances. What they found was that the expansion of the universe is accelerating. For most of cosmic history, it was assumed that the expansion was slowing down. Gravity, from all the matter in the universe, should be pulling things back together, decelerating the expansion. Eventually, the expansion might even reverse, leading to a big crunch where the universe collapses back on itself. But the observations showed the opposite. The universe's expansion is speeding up. Something is pushing the universe apart, counteracting gravity, causing space itself to expand faster and faster. We call this something dark energy, but we don't know what it is. Dark energy makes up about 68% of the universe's total energy. Dark matter, another mysterious substance we can detect through its gravitational effects, but can't see directly, makes up about 27%. All the normal matter, everything made of atoms, stars, planets, gas, dust, people, makes up only about 5%. We don't understand what 95% of the universe is made of. Dark energy is the most mysterious part. It appears to be a property of space itself. Every cubic meter of space has a certain amount of dark energy, and as the universe expands and more space is created, there's more dark energy. This is different from matter and radiation, which become diluted as space expands. If you have a certain number of particles in a box and you expand the box, the density goes down, but dark energy doesn't dilute. Its density remains constant, even as space expands. This means that as the universe grows larger, the total amount of dark energy increases, and its effect on the expansion becomes stronger and stronger. Eventually, dark energy will dominate completely. The universe's expansion will accelerate to the point where galaxies beyond our local group are receding from us faster than light. We'll lose sight of them, one by one, as they cross the cosmic event horizon. In the far future, hundreds of billions of years from now, any observers in our galaxy or the merged Milky Way Andromeda system will only be able to see our local group. Everything else will have been carried away by the expansion of space. The observable universe will shrink, not because space is contracting, but because distant objects are accelerating away from us faster than light can catch up. Eventually, the observable universe from our location might contain only our local galaxy cluster. Beyond that, total darkness. No distant galaxies, No cosmic microwave background visible from newly distant regions. Just the local group and empty expanding space. This is sometimes called the Big Freeze or the heat death of the universe. It's one possible fate of the cosmos. The expansion continues forever, driven by dark energy, and the universe becomes colder, darker, more diffuse. Stars burn out, galaxies fade, and eventually only black holes remain. Those black holes evaporate through Hawking radiation over unimaginably long timescales, 10 to the 100 years or more. And finally, the universe reaches thermal equilibrium, a state of maximum entropy where no energy gradients exist and nothing can happen. But this fate depends on the nature of dark energy. If dark energy is truly constant, a property of space called the cosmological constant, then yes, this is the future. But if dark energy is something else, something that can change over time, then the future might be different. Some models suggest dark energy might increase, causing the expansion to accelerate even faster. In the most extreme scenario, called the Big Rip, the expansion becomes so rapid that it tears apart galaxies, then solar systems, then planets, then atoms themselves. Space-time would be ripped to shreds in a finite time, perhaps 20 billion years from now. Other models suggest dark energy might decrease or even reverse, turning into an attractive force. This could slow the expansion and eventually reverse it, leading to a big crunch after all. We don't know which scenario is correct, because we don't understand what dark energy is. It's the most important unsolved problem in cosmology, and solving it would tell us not just about the future of the universe, but about the nature of space itself. And it connects to the question of what lies beyond the edge. If dark energy is a property of space, then it exists everywhere, not just in our observable universe. Beyond our cosmic horizon, in the unobservable regions of the universe, dark energy is pushing space apart. If we could somehow see those regions, we'd see the same accelerating expansion. The edge of the observable universe isn't an edge in the physics. The laws are the same beyond the horizon as they are here. Dark energy operates everywhere, inflating space, carrying distant regions away from each other at ever-increasing speeds. And in the multiverse scenarios, dark energy might vary from one bubble universe to another. Our universe has a small positive dark energy that causes accelerating expansion. Other universes in the landscape might have larger values, causing faster expansion, or negative values, causing contraction, or zero, leading to a coasting universe that expands but doesn't accelerate. The amount of dark energy might be one of the environmental variables that differs from bubble to bubble, and most values would be hostile to structure formation. Too much dark energy, and the universe expands so fast that galaxies can't form. Too little or negative dark energy, and the universe recollapses before stars can form. Our universe has just the right amount to allow billions of years of structure formation before the expansion accelerates significantly. This is another example of apparent fine-tuning that the anthropic principle might explain. In a multiverse with different values of dark energy, only in bubbles with the right amount do observers arise to measure it. So, where does that leave us? What can we actually say about what lies beyond the edge of the universe? The honest answer is we don't know. We have ideas, theories, possibilities, but no certainty. The edge of the observable universe is a horizon of ignorance, a boundary between what we can know and what we can only speculate about. But here's what we do know. The observable universe is vast and filled with structure. Galaxies, stars, planets, matter, and energy organized in intricate patterns. We can map this structure with incredible precision. The Sloan Digital Sky Survey has mapped millions of galaxies, creating a three-dimensional picture of the cosmic web. We can see the filaments of galaxies stretching across hundreds of millions of light-years. We can see the voids between them, vast empty regions where galaxies are rare. We can trace the distribution of matter back to the tiny fluctuations in the CMB and forward to the large-scale structure we see today. And it all matches. The predictions from inflation and gravitational collapse match the observations to extraordinary precision. The laws of physics that govern this structure, gravity, electromagnetism, the strong and weak nuclear forces, appear to be the same everywhere we look, as far out as we can see. We've measured the spectra of light from distant galaxies billions of light-years away, and the patterns match what we expect from the same atoms behaving according to the same laws. Carbon absorbs light at the same wavelengths in distant galaxies as it does in laboratories on Earth. Hydrogen's emission lines have the same ratios. The laws don't appear to change with distance or time, at least not in any way we can detect. This is remarkable because it's not obvious that it should be true. The laws could have been different in the early universe or in distant regions. But as far as we can tell, the physics is universal. The same rules apply everywhere in the observable universe. The universe had a beginning, the Big Bang, about 13.8 billion years ago. We know this from multiple independent lines of evidence. The expansion of the universe, which we observe directly. The cosmic microwave background, which matches the predictions of a hot early state. The abundance of light elements like hydrogen, helium, and lithium, which match what we calculate should have been produced in the first few minutes after the Big Bang. And the ages of the oldest stars, which are consistent with a universe that's 13.8 billion years old. Before that, we don't know. Our equations break down at the Big Bang singularity. General relativity predicts infinite density and temperature, which is a sign that the theory is incomplete. We need quantum gravity to understand what really happened at the beginning, and we don't have a complete theory of quantum gravity yet. The universe is expanding, and that expansion is accelerating due to dark energy. We've measured this in multiple ways. By observing distant supernovae and seeing they're farther away than they should be if the expansion were slowing down. By measuring the rate of expansion at different distances and times. By analyzing the cosmic microwave background and the large-scale structure of the universe. All the evidence points to accelerating expansion driven by something we call dark energy. We don't understand what dark energy is, but we can measure its effects. It makes up about 68% of the universe's total energy. Dark matter, which we detect through its gravitational effects but haven't identified, makes up about 27%. Normal matter, everything made of atoms, is only about 5%. This means 95% of the universe is made of things we don't understand. That's humbling and exciting. It means there's a vast amount left to discover. Beyond our cosmic horizon, there is almost certainly more universe. Whether it's finite or infinite, whether it's part of a multiverse or a cyclic cosmos, whether there are extra dimensions or parallel realities, we don't know. But the fact that we can ask these questions, that we can push the boundaries of knowledge to the very edge of the cosmos and beyond, is extraordinary. Humans have gone from thinking the Earth was the center of everything to understanding that we live on a small planet orbiting an ordinary star in one galaxy, among trillions. We've gone from thinking the Milky Way was the entire universe to discovering there are 2 trillion galaxies beyond it. We've gone from thinking the universe was eternal and unchanging to discovering it had a beginning and is expanding. We've gone from thinking we could see everything to realizing there's an entire universe beyond our horizon that we can never observe. Each step in this journey has been humbling and awe-inspiring, and we're not done yet. The next generation of telescopes and experiments will probe deeper into space and time. The James Webb Space Telescope, which launched in 2021, is already observing the most distant galaxies ever seen. Galaxies that formed when the universe was only a few 100 million years old. It's studying the atmospheres of exoplanets, looking for signs of water, oxygen, and other molecules that might indicate life. It's mapping the distribution of dark matter by observing how it bends light from background galaxies. Ground-based telescopes are getting larger and more sophisticated. The extremely large telescope in Chile, when completed, will have a primary mirror 39 meters across, almost 4 times larger than the largest current telescopes. It will be able to observe fainter and more distant objects than any previous telescope. The Vera Rubin Observatory, also in Chile, will survey the entire visible sky every few nights, creating a time-lapse movie of the universe. It will discover millions of new galaxies, asteroids, and transient events like supernovae. It will map the distribution of dark matter across the cosmos. These telescopes will help us understand the large-scale structure of the universe, how galaxies form and evolve, and how dark energy is affecting the expansion. We'll measure the cosmic microwave background with greater precision, looking for subtle signatures of inflation or evidence of other universes. Multiple experiments are searching for B-mode polarization in the CMB, the signature of primordial gravitational waves. If we detect it, it would confirm inflation and tell us about the energy scale at which it occurred. We'll search for gravitational waves from the early universe, ripples in space-time that might carry information from the first moments after the Big Bang. Ground-based detectors like LIGO and Virgo have already detected gravitational waves from merging black holes and neutron stars. Space-based detectors like LISA, planned for launch in the 2030s, will detect lower-frequency gravitational waves from supermassive black hole mergers and possibly from cosmic strings or other exotic phenomena. And we'll build particle accelerators to recreate the conditions of the early universe in the lab, testing our theories of physics at the highest energies. The Large Hadron Collider has already discovered the Higgs boson and is continuing to search for new particles and forces. Future colliders might reach even higher energies, probing deeper into the fundamental nature of matter and forces. We'll develop new theories, new mathematical frameworks, that might finally unify general relativity and quantum mechanics, and tell us what really lies beyond the edge. String theory, loop, quantum gravity, and other approaches are being actively developed. Progress is slow because the mathematics is incredibly complex, and the energy scales involved are far beyond what we can test directly. But theoretical physicists are making advances, finding connections between different approaches, and developing new computational techniques to solve previously intractable problems. And we're looking for life beyond Earth. Thousands of exoplanets have been discovered orbiting other stars. Many of them are in the habitable zone, where liquid water could exist on the surface. We're beginning to study the atmospheres of these planets, looking for biosignatures, molecules like oxygen and methane that might indicate biological activity. SETI, the search for extraterrestrial intelligence, continues to scan the skies for signals from other civilizations. No confirmed signals have been found yet, but the search is expanding, using more telescopes and covering more of the electromagnetic spectrum. If we found evidence of life elsewhere in the universe, it would transform our understanding of our place in the cosmos. If life is common, then the universe might be teeming with it, and we're just one example among countless others. If life is rare, then Earth becomes even more precious, a rare jewel in a vast cosmic desert. Either answer would be profound. These observations and experiments won't answer every question about what lies beyond the edge. Some questions might be fundamentally unanswerable because the regions we're asking about are forever beyond our reach. But every discovery pushes the boundary a little farther. Every new observation gives us a clearer picture of the universe we inhabit, and every theoretical breakthrough brings us closer to understanding the deepest nature of reality. But even if we never observe what's beyond our cosmic horizon, even if it remains forever hidden, the quest to understand it is valuable. Because the question, what's beyond the edge, is really a question about the nature of reality itself. It's a question about what exists, how it came to be, and what it all means. And pursuing these questions, even knowing we might never find complete answers, is part of what makes us human. Humans are explorers by nature. We've always pushed beyond the known into the unknown. Our ancestors left Africa and spread across the globe, crossing oceans and mountains to reach every continent. We've climbed the highest peaks, descended to the deepest ocean trenches, ventured to the poles. We've sent spacecraft to every planet in the solar system and beyond, to the Kuiper Belt, to interstellar space. Voyager 1, launched in 1977, is now more than 15 billion miles from Earth, the farthest human-made object, still sending back data from the space between stars. This drive to explore isn't just about practical benefits. It's about curiosity, about the desire to know what's out there, to see what's beyond the next horizon. And now, with telescopes and mathematics, we're exploring realms that no spacecraft will ever reach. We're probing the edge of the observable universe, looking back in time to the first moments after the Big Bang. We're theorizing about what lies beyond, regions of space we can never visit, universes we can never observe. The tools have changed from ships and compasses to telescopes and equations. But the spirit is the same. We want to know. We need to understand. It's in our nature. And this quest has practical value, even when the immediate applications aren't obvious. The mathematics developed to understand general relativity and quantum mechanics gave us GPS, nuclear power, semiconductors, and countless other technologies. The space race gave us satellites, telecommunications, weather forecasting, materials, science, advances. Astronomy gave us CCDs, the image sensors in every digital camera and smartphone. Medical imaging techniques like MRI and PET scans came from physics research. The World Wide Web was invented at CERN, the particle physics laboratory, to help physicists share data. When we pursue fundamental questions about the universe, we never know what practical applications will emerge, but history shows that they do emerge, often in unexpected ways. The knowledge we gain from studying the edge of the universe and what lies beyond might seem abstract and impractical. But it expands our understanding of gravity, space-time, quantum mechanics, and the fundamental nature of reality. And that understanding has a way of leading to technologies we can't yet imagine. Beyond the practical benefits, There's intrinsic value in understanding. We're part of the universe, made of the same matter, governed by the same laws. When we study the cosmos, we're studying ourselves, our origins, our place in the grand scheme. The atoms in our bodies were forged in stars billions of years ago. The calcium in our bones, the iron in our blood, the oxygen we breathe, all were created in stellar furnaces or supernova explosions and scattered into space to eventually become part of us. We are literally made of stardust. That's not poetry, it's physics. The cosmos is not separate from us. We're part of it, a way for the universe to know itself. Through our observations and our theories, the universe is becoming self-aware. Matter has organized itself into complex structures, brains, minds, civilizations, capable of understanding the laws that govern matter. That's extraordinary. It might be common in the universe, or it might be rare. We don't know. But either way, it's remarkable. And it means that when we ask what's beyond the edge of the universe, we're asking on behalf of the universe itself. We're the universe's way of exploring its own boundaries, of questioning its own nature. There's a poetic symmetry to that. The universe creates observers, and those observers study the universe, including the question of what lies beyond the observable limits. It's a self-referential loop, consciousness arising from matter to contemplate matter and space and time. Some physicists and philosophers have argued that this self-awareness might be inevitable. If the universe is infinite, or if there's a multiverse, then somewhere, conscious observers must arise. The laws of physics allow for complexity, and complexity eventually leads to life and consciousness. It might take billions of years and require very specific conditions, but in an infinite cosmos, it will happen. And once it happens, those conscious beings will do what we're doing now. They'll look up at their sky, wonder what's out there, build theories, conduct experiments, push the boundaries of knowledge. The universe might be full of civilizations asking the same questions we're asking, wondering what's beyond their observable horizon, theorizing about multiverses and extra dimensions, searching for a theory of everything that unifies all the forces and explains all the phenomena. We might all be part of a vast cosmic community of observers, each one probing the nature of reality from their own unique vantage point. Or we might be alone. Earth might be the only place in the observable universe where life has arisen and evolved to the point of asking these questions. That would make us incredibly rare and precious. The only beings capable of understanding the cosmos, at least in our corner of space and time, either possibility is profound. If we're common, then consciousness is a fundamental feature of the universe, something that emerges wherever conditions allow. The universe is, in a sense, alive, with minds contemplating existence. If we're rare, then we have a special responsibility. We might be the only way the universe knows itself, the only observers capable of understanding what exists and why. Every discovery we make, every question we answer, every theory we develop, is a gift to the cosmos, a way for reality to understand its own structure. This perspective changes how we think about our place in the universe. We're not separate from the cosmos, looking at it from the outside. We're part of it, a way for it to experience itself. The boundary between observer and observed dissolves. We are the universe observing itself. And when we ask what lies beyond the edge, we're asking a question the universe is asking about itself through us. There's a humility in this perspective. We're small, temporary, fragile. Our lives are brief flickers in cosmic time. Our planet is a speck in an incomprehensibly vast space. But there's also a grandeur. We're part of something larger than ourselves, part of a cosmic story that began 13.8 billion years ago and will continue for trillions of years into the future. We're made of the universe, and we can understand the universe. That's a privilege and a responsibility. Is the universe finite or infinite? Is it one of many or the only one? Did it have a beginning, or has it always existed in some form? Are the laws of physics fixed, or do they vary from place to place, from universe to universe? These are the deepest questions we can ask, and they touch on philosophy, metaphysics, and the very meaning of existence. Consider the question of infinity. If the universe is infinite, then it contains an infinite amount of matter and energy. Infinite galaxies, infinite stars, infinite planets. The human mind struggles with infinity. We can work with it mathematically, but we can't truly visualize it or grasp it intuitively. An infinite universe would mean there's no center, no edge, no special location. Every point in an infinite universe looks the same as every other point on average. You could travel forever in any direction and never reach an edge or a boundary. And as we discussed earlier, in an infinite universe with a finite number of possible configurations of matter, every possible configuration must repeat. Every possible world exists somewhere. Every version of history, every choice, every outcome. This has profound implications for free will and meaning. If every choice you could make is made by some version of you somewhere in the infinite universe, then in what sense are your choices yours? In what sense does anything matter if all possibilities are realized? Some philosophers find this troubling. Others find it liberating. If every possibility exists, then every version of you gets to experience their own unique reality, and the choices you make determine which version you experience, even if other versions make different choices elsewhere. Now, consider the opposite scenario: a finite universe. If the universe is finite, then there's a specific amount of matter and energy, a specific number of particles, a specific size. It's still unimaginably vast, but it's bounded. A finite universe feels more comprehensible, more manageable. There's a totality to it. You could, in principle, count everything in it. You could, in principle, know everything about it. But a finite universe raises its own questions. If the universe is finite, what's beyond it? If space has an edge, what's on the other side? The answer, according to general relativity, is that there is no beyond, no other side. Space is all there is, and if it's finite, it curves back on itself. But that's hard to accept intuitively. We're used to thinking of things as being inside other things, contained by larger structures. A finite universe that isn't contained by anything challenges our intuitions about space and existence. Then there's the question of time. Did the universe have a beginning? The Big Bang suggests it did, 13.8 billion years ago. But what does it mean for time to have a beginning? Before the Big Bang, there was no before, because time itself didn't exist. The question, what happened before the Big Bang, is meaningless if time began at the Big Bang. It's like asking what's north of the North Pole. The question doesn't make sense because north is defined by the Earth's rotation, and at the North Pole, every direction is south. Similarly, before is defined by the flow of time, and if time began at the Big Bang, there's no before. But our intuition rebels against this. Surely, we think, something must have come before. Surely the Big Bang must have been caused by something. Quantum mechanics offers a possible answer. In quantum mechanics, things can happen without a cause. Particles can pop into existence from nothing, borrowing energy from the vacuum as long as they disappear quickly enough. Perhaps the universe itself popped into existence from nothing, a quantum fluctuation on the grandest scale. This is the idea of a universe from nothing, proposed by physicists like Lawrence Krauss and Stephen Hawking. In this scenario, the universe doesn't need a cause. It's a quantum event, governed by probability rather than causality. But even this raises questions. If the universe came from nothing, where did the laws of quantum mechanics come from? The laws themselves are something, not nothing. They're mathematical structures that describe how particles and fields behave. If the universe came from nothing via quantum processes, then those processes and the laws governing them must have existed before the universe. But how can laws exist without a universe for them to apply to? This is one of the deepest mysteries in cosmology and philosophy. The origin of the laws of physics. Why these laws and not others? Why any laws at all? Some physicists, like Max Tegmark, have proposed that the universe is mathematics. Not that it's described by mathematics, but that it literally is a mathematical structure. In this view, the laws of physics aren't separate from the universe. They are the universe. The universe is the physical instantiation of a particular mathematical structure, and all possible mathematical structures exist as universes somewhere in the ultimate multiverse. This mathematical universe hypothesis pushes the idea of the multiverse to its logical extreme. Not just different regions of space or different bubble universes, but different mathematical structures altogether. Some universes would have 3 dimensions, some would have 10, some would have particles and forces like ours, some would have completely different entities. Some would be simple, some complex. All possible mathematical structures would exist as physical realities. If this is true, then the question why these laws isn't really a question about physics. It's a question about mathematics and existence. The laws are what they are because this particular mathematical structure is the one we find ourselves in. And we find ourselves in it because it's one of the structures that allows for observers. Most mathematical structures wouldn't support complexity or consciousness. They'd be too simple, too chaotic, too unstable. But in the infinite space of possible mathematical structures, some would allow for stars, planets, and life. And only in those structures would beings exist to ask why the laws are what they are. This is the anthropic principle taken to its ultimate conclusion. We observe these laws because only these laws, or laws like them, allow us to exist. Whether this is a satisfying explanation depends on your philosophical perspective. Some find it elegant and profound. Others find it empty, a non-answer to the question of why. There's also the question of consciousness and observation. In quantum mechanics, observation plays a crucial role. The wave function collapses when an observation is made, determining the outcome of a quantum event. But what counts as an observation? Does it require a conscious observer, or is any interaction with a macroscopic system sufficient? In the many worlds interpretation, this question is avoided because the wave function never collapses. All outcomes occur, and consciousness simply experiences one branch. But in other interpretations, the role of the observer is more puzzling. Some physicists, like John Wheeler, suggested that observers play a fundamental role in bringing the universe into existence. In Wheeler's participatory universe, the act of observation doesn't just reveal reality, it creates it. The universe exists in a quantum superposition until observers measure it, and through those measurements, observers give the universe definite properties. This leads to a strange loop. The universe creates observers through billions of years of evolution. Those observers then make measurements that collapse the wave function and give the universe its properties. In a sense, the universe creates the observers who create the universe. It's a self-referential loop that challenges our usual notions of causality. If this is true, then consciousness isn't just a byproduct of physical processes. It's a fundamental part of the cosmic story, the mechanism by which reality crystallizes from quantum possibility. This is deeply speculative and controversial, but it connects to profound questions about the nature of mind and matter, subjective experience, and objective reality. What is consciousness? How does it arise from matter? Why does it feel like something to be conscious? These questions, known as the hard problem of consciousness, remain unsolved, and they intersect with cosmology in unexpected ways. If observers play a role in collapsing the wave function, then the existence of consciousness might be a cosmological fact, not just a biological one. The universe might require observers to fully exist. And if that's true, then the edge of the universe takes on a new meaning. Beyond the observable universe, in regions that can never be observed, does reality exist in the same way? If observation is necessary to collapse quantum possibilities into definite states, then unobservable regions might exist in a superposition, a quantum fog of unrealized possibilities. They would only become real if and when observers could reach them and make measurements. This is pure speculation, but it shows how questions about the edge of the universe connect to the deepest mysteries in physics and philosophy. What is real? What does it mean to exist? What role does consciousness play in the cosmos? These aren't just abstract philosophical questions. They're questions that arise naturally when we push our understanding to the limits of what we can know. The edge of the universe is not just a physical boundary. It's a boundary of knowledge, a line between what we can know and what might forever remain a mystery. But that boundary is not fixed. It moves as our knowledge grows. Every discovery, every new observation, every breakthrough in theory pushes the boundary a little farther. We may never know everything about what lies beyond the edge, but we can keep pushing, keep exploring, keep asking. That's what humans do. We explore. We question. We seek to understand. From the first humans who looked up at the night sky and wondered what those lights were, to the astronomers who built telescopes and discovered galaxies, to the physicists who developed theories of relativity and quantum mechanics, to the cosmologists mapping the large-scale structure of the universe, we've been on a journey to understand our place in the cosmos. And that journey is far from over. The edge of the universe represents the frontier of that journey, the place where our knowledge ends and mystery begins. And it's a reminder that no matter how much we learn, there will always be more to discover, more questions to ask, more mysteries to explore. Let me leave you with one final thought. The observable universe, the part we can see, is already so vast that it defies comprehension. 2 trillion galaxies, each with hundreds of billions of stars spread across 93 billion light-years. The numbers are so large, they become abstract. We can write them down, calculate with them, but we can't truly grasp them intuitively. 1 billion is a number we can barely comprehend. 1 billion seconds is about 31.5 years. 1 billion stars would fill a galaxy. but we're talking about hundreds of billions of stars per galaxy and 2 trillion galaxies. The scale is beyond human intuition. And if that's just a tiny fraction of the total universe, if beyond our horizon lies an infinite expanse, then the true scale of reality is beyond anything we can imagine. Or if there's a multiverse of bubble universes, each one as large as our observable universe, or larger, each with different laws and properties, then reality encompasses not just more space, but more possibilities, more ways for existence to manifest. Or, if there are parallel worlds branching from every quantum event, then reality includes not just the universe we observe, but all possible versions of it, all possible histories, all possible futures. The scope is staggering. We are unimaginably small, living on a tiny planet, orbiting an ordinary star in one galaxy among trillions. Our entire observable universe might be just one bubble in an infinite foam of universes. Our entire history, from the Big Bang to the present, might be just one branch in an infinite tree of quantum possibilities. Every moment of human history, every thought, every achievement, happens in a cosmic context so vast it makes our concerns seem trivial. But we are also extraordinary. Despite our smallness, despite our brief existence, we can think about these things, understand them, at least partially, and keep pushing the boundaries of what's knowable. We've gone from huddling in caves, afraid of the dark, to mapping the cosmos, understanding the Big Bang, theorizing about the multiverse. In a few thousand years, we've progressed from thinking the Earth was flat and the stars were lights on a dome, to understanding that we live in an expanding universe that might be one of many. That's remarkable. It speaks to the power of curiosity, reason, and the scientific method. The edge of the universe is out there, a horizon we can approach but never quite reach. It's 13.8 billion light-years away in every direction, marked by the cosmic microwave background, the oldest light we can see. Beyond it lies mystery, perhaps infinite space, stretching forever, filled with galaxies we'll never see. Perhaps a finite universe that curves back on itself, with no beyond at all. Perhaps other universes, bubble universes from eternal inflation, each with different physical laws. Perhaps parallel realities branching from quantum events, infinite versions of us making different choices. Perhaps extra dimensions we can't perceive, with our three-dimensional universe embedded in a higher dimensional space. Perhaps something we haven't even conceived of yet, some aspect of reality that our current theories don't capture. We don't know what's beyond the edge. We might never know with certainty. Some aspects of reality might be forever beyond our reach, hidden behind horizons we can never cross. But the fact that we can ask the question, that we can explore the possibilities, that we can push our understanding to the very limits of the cosmos, that's what makes us human. The universe might have an edge, but human curiosity does not. We will keep looking, keep questioning, keep wondering. We'll build better telescopes to see farther into space and deeper into time. We'll develop better theories to explain what we observe and predict what we haven't yet seen. We'll keep pushing the boundary between the known and the unknown. And even if some questions remain unanswered, even if some mysteries persist, the journey is worthwhile. The quest to understand is its own reward. Because in seeking to understand the universe, we come to understand ourselves. We learn where we came from, how we got here, what we're made of. We discover that we're not separate from the cosmos, but part of it. We're stardust that has learned to wonder about stars. We're the universe's way of knowing itself. And that's beautiful. it gives meaning to our existence. Not a meaning imposed from outside, but a meaning that emerges from our connection to the cosmos. We matter because we're part of something larger. We matter because we can think and feel and understand. We matter because we can ask what lies beyond the edge and have the courage to seek answers. So, when you look up at the night sky tonight, think about what you've learned. The stars you see are part of our galaxy, the Milky Way, one of 2 trillion galaxies scattered across the observable universe. Beyond those galaxies, beyond the farthest reaches of space we can see, lies the edge, the cosmic horizon, the boundary of observation. And beyond that edge lies something, more universe, or other universes, or extra dimensions, or something stranger still. We don't know. But we're working on it. Generation by generation, we're pushing farther, understanding more, mapping reality with ever greater precision. The edge is out there, waiting. And one day, perhaps, we'll understand what lies beyond it. Or perhaps we'll discover that the question itself needs to be reformulated, that our concepts of space and time and existence break down at the edge, and we need new ways of thinking to comprehend what's really there. Either way, the journey continues. The universe has an edge, a horizon beyond which we cannot see. But that edge is not a wall. It's an invitation. An invitation to keep exploring, keep questioning, keep wondering about the deepest mysteries of existence. Because even if we never know for certain what lies beyond the edge, the quest to understand is what makes us who we are. It's what makes us human, and it's what connects us to the cosmos in the most profound way possible. We are the edge. We are the place where the universe becomes aware of itself, where matter organizes into minds capable of contemplating matter. We are the boundary between the known and the unknown, the observers who bring reality into focus through our measurements and our theories. And we are the explorers who push that boundary farther with each discovery, with each new insight, with each question answered, and each new question raised. The edge of the universe is not just out there in space. It's here, in our minds, in our capacity to wonder and to know. It's the horizon of understanding, always receding as we approach it, always revealing new vistas beyond. So, when you look up at the night sky tonight, remember that you're looking out at the observable universe, the part we can see. But beyond that visible horizon, beyond the farthest galaxies and the cosmic microwave background, beyond the very edge of space and time, there's something else. We don't know what, but it's out there, waiting to be understood. And perhaps someday, future generations will push past the boundaries that limit us now and discover what lies beyond the edge of the universe. Until then, we can keep looking up, keep wondering, and keep exploring the cosmos with awe and curiosity. Because the universe might have an edge, but human curiosity does not. Thank you for joining me on this journey to the edge of everything. If you found this exploration thought-provoking, please consider liking this video and subscribing to the channel. Your support helps me continue making these deep dives into the mysteries of space and existence. And remember, the edge of the universe is not the end of the story. It's just the beginning of a new chapter in our quest to understand reality. Sleep well tonight, knowing that you exist in a cosmos far stranger and more magnificent than we ever imagined. The universe has an edge, but beyond that edge lies the greatest mystery of all, and we're only just beginning to explore it.